he is a specialist of stochastic partial differential equations and fractional diffusion. So,
yes, give me a sec. Yes, so
okay.
Can you see my screen?
Yes, yes, you can start.
Okay, so first of all, thank you for the organizers for inviting me and giving me the opportunity to give a talk here. And it's a shame that I cannot be there in person, but probably this is the next best thing. So this is a joint work with Erika Hausenblas and Krisztosi Fahim. And my talk is about some approximation results for mild solutions of stochastic fractional order PDEs driven by Gaussian noise. So the formulation of the problem is that in general, we consider an integral equation of the form ut equals x naught plus a deterministic convolution plus a stochastic convolution. And an abstract approximation sequence, which is given by UN, and UN solves a very similar equation with the same data, but different operator families, S1n and S2n. So here, WH is an H-cylindrical Wiener process, where H is a real separable Hilbert space. And so if you're not familiar with the stochastic PDEs, then you can think of WH as being given by an orthogonal sum, where you take an ON basis of this Hilbert space H, and you put an independent real-valued Brownian motion on every coordinate. So this is how WH is given formally. And so the problem with this formulation is that this series does not converge, for example, in the L2 sense. But the good news is if the integrand is sufficiently nice, you can still integrate with respect to such an object. So in this equation, the S1 and S2, they are operator families, so that they are deterministic. And the crucial property of these families that we are going to use, that they admit certain smoothing estimates with respect to certain Hilbert spaces, H1 and H2. So H0 is a third Hilbert space. So this is the state space for the equation. So this is where the values of U and UN will be. The nonlinear functions, so the data G and F, they are assumed to be standard, so as nice as possible, meaning that they are going to be globally Lipschitz and satisfying a linear growth condition in the state variable. So here G is an operator valued family, so it maps 0T and the state space H0 into the space of Hilbert-Schmidt operators from H to H1. So this is needed for stochastic integration. So the goal is to derive error estimates for the difference U minus UN. So both of them are random variables with values in H0 in certain norms, namely in the LP omega C gamma norm, and in particular in the LP C0T H0 norm. Assuming that one has access to deterministic error estimates to the deterministic operator families, and also error estimates for the derivative of the difference. So here, the norm, the C gamma norm, is just the standard Hölder semi-norm, and where gamma is 0, so when we are in the C setting, then this is just the supremum norm. In general, this is it turns out to be a rather non-trivial task, because the stochastic convolutions fails to be a semi-martingale. So, for example, Dub's inequality or other maximal type inequalities cannot be used to derive error estimates in such norms. So here the important thing is that the supremum is inside the expectation. So you take the supremum first, and then the expectation is outside. So if one proves error estimates in this norm, then one gets pathwise error estimates. So this is much stronger than if I would put the expectation inside. And these estimates, they are crucial when one wants to derive error estimates for equations when the data are not globally Lipschitz. So if one wants to use localization arguments, then one needs these pathwise error estimates. So even so as I said, the stochastic convolution is not sufficiently nice to have standard maximal type estimates. Even when the operator families have the semigroup property, so when we do not have a non-trivial memory term, then one can use the so-called factorization method and then work out error estimates. It's still much more complicated than the standard error estimates when I had the expectation inside the soup. But in general, for example, if one considers fractional order equations, then the semigroup property also fails. So even the direct application of the factorization method does not work. So a particular situation which leads to such abstract equations that I've written in the first slide is if one considers a general fractional order stochastic evolution equation of this form, where ut equals some initial data and an operator a times a fractional integral plus a fractional integral of a deterministic f plus a fractional integral of a stochastic term. And here we assume that a is as nice as possible. So it's density defined, possibly unbounded. And when I say possibly, I mean usually unbounded. Non-negative operator on the Hilbert space H naught. The parameter alpha is between 0 and 2. And kappa is larger than 0 and beta is larger than half. So this condition here is needed so that the integral here makes sense. Otherwise, we have a very, so when one defines stochastic integrals with respect to infinite dimensional linear processes, one still has an Ito isometry. So the integrand has to be L2 in time with respect to a certain norm. And if beta is less than half, then this will have a too much singularity if I raise it to a power 2. So this is where this condition comes in. So with these parameters, I can regulate the time regularity of the stochastic and the deterministic feedback. Now, this general equation contains many special cases. So if I take alpha equals beta equals kappa equals 1, so all the parameters are 1, then I will just get the standard stochastic heat equation. If I take the parameter alpha between, and in this case, the U1 is 0. If I take the parameter alpha between 0 and 1, then again I take U1 equals 0 in this case, then I will get a fractional stochastic heat equation. And then when I take alpha between 1 and 2, then I will get a fractional stochastic wave equation. So this is the motivating example by considering the equations in the first slide, because the mild solution of such equations are going to be written in that form. But I will have this as an example a little bit later. So the main assumptions that we work with is that I already mentioned some of it. So the diffusion coefficient G is Lipschitz continuous, and it's of linear growth in the state variables, which is the second variable. F is also Lipschitz continuous, and it's linear growth again in the state variable. So this is standard globally Lipschitz assumptions. And the initial process is predictable, and then more importantly, for some p larger than 2, it belongs to this space, so this is p integrable with values in L infinity. And for the operator families, I suppose that they admit certain smoothing properties with respect to these Hilbert spaces H1 and H2. And namely, I can bound the operator family and its derivative by an integrable function, and I can put here weights t to the gamma 1 and t to the gamma 1 minus 1. So here the derivative, since I have a derivative here, I'm not going to consider here a minus 1. And I have a similar type of estimate for the operator which appears in the stochastic convolution. The only difference between the two, that the coefficient, the exponents here for the deterministic convolution can go up to 1, and for the stochastic convolution only go to 1/2. So this is the smoothing property of the operators, the deterministic operator families appearing in the deterministic and the stochastic convolution. And in order to formulate the rate assumption about the approximating operator families, I consider the difference between the deterministic operator family and its approximation, and I put here a weight function, and this is Rn, and I have two families, so this I'm going to have an R1 and R2. So this is the difference, and then I put here a rate. And again, what I assume that I have the same type of error estimate. So if I put here this operator family, and I put here the derivative, and so this is the difference with the weight, with the rate. Then again, this is uniformly bounded in N by an L1 function times X in this H1 space. So again, this translates to that I have so-called, usually so-called non-smooth error estimates. But the new thing here that I not only require the non-smooth error estimate for the operator families, but I also require non-smooth error estimates for the derivatives. And I need this both for both families. And then the main result is that if I have these two parameters, gamma 1 and gamma 2, so these are the parameters that appear in the smoothing estimates, both for the operator families and the approximation. And if the initial approximations are uniformly bounded, say by k, and I consider the error between ut and unt, so this is the original process and this is the approximating process, and I denote by E naught the difference between the initial terms. And then one can derive, one has error estimates for E in the C gamma norm, in the LP omega C gamma norm, which is bounded by the C gamma norm of the initial terms, plus the LP norm of E of 0, plus the two rates that appear in the deterministic error estimate. And then one gets this similar estimate for in the C norm. So this is the E sup norm. Again, it's a little bit simpler, so that I will have the LP omega C norm of the initial term plus R1 and R2. So these are the two rates that appear in the deterministic error estimate. So the message here is, if one has access to deterministic error estimates, both for the operator families and the derivative, then one can write down an error estimate directly in the C gamma norm for the stochastic processes. So you can actually read off the rate from the deterministic rates. Now, I'm not going to do the proof because it's beyond the scope of this talk. So the idea is that one uses, one looks at the deterministic and the stochastic convolution as Laplace multipliers between appropriate spaces. And then one uses a multiplier theorem to estimate the multiplier norm of these convolutions. And if you are a little bit familiar with multipliers and you think of Michlin's theorem, then if you use the Michlin multiplier theorem, that uses the function itself and its derivative. So it is very analogous. It's a little bit more complicated, but the idea is very similar to view these as multipliers. So instead of proofs, I'm just going to do a lot of examples. So this general theorem can be used to derive error estimates for spatial approximations in particular. And the simplest example of such a procedure is the spectral Galerkin method. So if I denote by lambda n the eigenvalues of A arranged in a non-decreasing order with corresponding orthonormal eigenbasis En, and then I denote by Hn the span of the first n eigenfunctions, and I denote by Pn the orthogonal projection onto Hn, so Pn is given by this orthogonal sum. And then I consider a special case of my abstract equation, u of t equals s alpha 1 ut u naught plus s alpha 2 u1, plus deterministic convolution plus a stochastic convolution. So this is by definition the mild solution of the equation that I've written down, this general fractional order equation, where f and g do not depend explicitly on t. So I did this just for the simplicity. And here, these operator families, the S alpha beta, which appear here, 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 and here, it is not that easy to write down explicitly, but it's a Laplace transform is very easily written down. So the Laplace transform of this operator family S alpha beta is given by z to the alpha minus beta and z to the alpha plus a inverse x. And then here I assume that the initial data are random variables which are sufficiently highly integrable. So they are in LP. All right, so by definition, this is the mild solution of my fractional order, general fractional order equation, where f and g do not depend on explicitly on time, only through the solution. So in this situation, I define my approximating operators S alpha beta n, and of course also S alpha kappa of n, just by taking the solution, the deterministic operator family, and multiply it by the orthogonal projection Pn. So this is going to be S alpha beta of n. And then my approximating process satisfies the same equation as before, replacing S alpha kappa and S alpha beta by the processes indexed by n. And so this is the simplest spatial approximation process one can think of. And then in this case, so what is the rate function? The rate function is going to be actually lambda to the minus nu n plus 1. So this is the n plus first eigenvalue of a to a power nu. So this is 1 divided by the first rate function. This is 1 divided by the second rate function. And this can be written as, again, this lambda to the n plus 1. And then since Sn is just a orthogonal projection of S alpha beta, then this is just given in such a simple form. And the same thing is we write down for psi 2. And to get the simplest results, we set all these spaces h1, h2, and h0 to be equal to 0. So this is, so to say, the trace class setting. And I will show later that actually, if one wants to consider space-time white noise, then one has to choose these h1 and h2 differently from h0. So this is the simplest possible case. So in this case, one may derive smoothing estimates based on the parameters. So these families are bounded by t to the beta minus 1, and the derivative, you just lose 1. So you just have a worse singularity at 0. So you increase the singularity by 1 at 0. And the same thing happens with S alpha kappa. So here the kappa helps, and also here it helps. And the derivative introduces an additional singularity here. Now, to use the theory, I have these non-smooth data estimates. So remember, h0 equals to h1. So in order to have here an order nu, I'm going to have a singularity introduced, an additional singularity here by minus alpha nu, and here a minus alpha nu minus 1. Right? So the rate what I get here, I pay a price of an additional singularity. Now, all these estimates are based on, one can prove that these operator families satisfy the following estimates. I can hit the operator family by a to the xi, where xi is a parameter between 0 and 1. And if I put here xi, then I'm going to introduce a singularity of order alpha xi. And if I hit the derivative with a to the xi, the same thing happens here, and the minus 1 changes to minus 2. Now, if beta is, for example, 1 and alpha is 1, that's the heat equation, then these are well-known estimates for the heat semigroup. And then one can derive these in a very similar fashion for the general case. Now, the big difference between the heat equation and the general when alpha is not equal to 1 is that in general, the maximum amount of a to the xi that I can put on this operator family is 1. And for the heat equation, that's a very special case, then I can put here actually any xi. And the reason being because then I have the semigroup property. But in general, I do not have. So in general, this is the maximum amount of a to the xi that I can put here. Now, the rate comes from the rate for the Galerkin approximation, namely that if I take identity minus the orthogonal projection times a to the minus nu, then this can be bounded by lambda n to the minus nu. So this is a very, very simple estimate. It's very straightforward to show. So this is, so if I combine the smoothing with this basic estimate, then one can easily derive all these. So for the spectral Galerkin method, in order to derive non-smooth data estimates, both for the family and for the derivative, the only thing that one needs is actually the smoothing estimates for the operator families. Now, if one considers finite elements, which I'm not going to consider in this talk, but one could do it, it's also in our preprint, then this is a little bit more complicated. It does not follow directly from the smoothing estimates. One has to work a little harder, but it's still possible to do. So what is it that we get? So again, I just write down the simplest cases. So if I take the standard stochastic heat equation, which corresponds to alpha equals beta equals kappa equals 1, and one of the initial data is 0 in this case, then I get an error estimate in the LP omega C norm. So this is the E sup norm. With the rate lambda n plus 1 to the minus nu, when nu can be anything less than 1/2 minus 1 over p, provided the initial data is in LP. So if the initial data is deterministic, for example, then I can put here infinity and I will get a rate nu less than 1/2, which is expected. Now for the stochastic heat equation, the simplest one, where beta and kappa is 1 and alpha is a parameter between 0 and 1. Again, in this case, u1 is 0. Then I get an error estimate of order nu, when nu is less than the minimum of 1/2 minus 1 over p divided by alpha and 1, provided that u0 is, again, LP integrable with values in the domain of a to the nu. So here one sees that actually for the stochastic heat equation, one gets a better rate because alpha is a number between 0 and 1, but there is a rate which you cannot exceed, and this is the maximum rate for the method. So even though if alpha is less than 1/2 minus 1 over p, the rate cannot exceed 1. So if you start to decrease alpha from 1 all the way down to 0, you will see that the rate is getting better and better until you reach 1. And once you've reached 1, the rate is not going to increase. Now for the stochastic wave equation, the simplest one, again, I take beta equals kappa equals 1, and now the parameter alpha is between 1 and 2. Then I get a similar estimate in the E sup norm, where nu is less than 1/2 minus 1 over p over alpha, and here alpha is between 1 and 2, so this is never going to exceed 1. So this is, so to say, the global Lifshitz setting, and in order to show that actually this setting is flexible enough to treat space-time white noise, I consider a one-dimensional example. So this is written in an Ito form, du equals a times a convolution equals dWh, where WH is a cylindrical Wiener process with respect to L2 on 0, 1. So this is so-called space-time white noise. So I have nothing in front, so there's no coefficient here. And alpha is between 1 and 2, and beta of t is then a weakly singular integral. So this is probably the simplest stochastic wave equation that you can write down with space-time white noise. Now, in this case, one can introduce fractional order norms, which is just, I consider this quantity here, and then I define, and this S is a parameter which can be any real number, positive, negative. So when S is positive, then this is not going to converge for every V. When S is negative, then it will converge for every V. So for positive, for non-negative parameters S, then I define this space as H dot S, which is nothing else but the domain of A to the S, which are all elements from V where this quantity is finite. So this is equivalent to the graph norm of A to the S. And for negative order, so where minus S is negative, so H dot minus S is nothing else, but I take the space H naught, I put this norm on it, and I take the completion or the closure with respect to this norm. So I'm going to get something larger than H0. And then in this case, I have to take H1. So now this is not going to be H dot minus S for S larger than 1,4. So S can be anything larger than 1,4. Of course, the closer I take S to 1,4, the better the result will be. So in this case, I don't see anything here, but actually there's an identity here. So I'm going to define my coefficient G as just the constant G of X equals the identity, where I take the identity being the mapping which sends V to V, and then H1 in this case is larger than H0, so this makes sense. And then if I calculate the Hilbert-Schmidt norm of the identity from H0 to H1, then I just have to calculate this orthogonal sum. So I have to take an ON basis of H0, which I'm going to just going to take the eigenbasis of the Laplace operator, and then I evaluate this in the H dot minus S norm. And then in this case, then these quantities are just lambda k to the minus 2s. And then here I use the asymptotics of the eigenvalues of the Laplace in 1D with the initial boundary conditions, which is k squared. And then I see that this sum converges if and only if S is larger than 1,4. So this is why I need here a parameter which is larger than 1,4. So in this case, I really need this space H1, which is not H0, and then I can, using the smoothing property of the operator family, in this case I only have one because I don't have F, I only have G. And so what I'm going to see is that with respect to this larger space, I'm going to introduce a singularity of this order, and I'm going to introduce the same singularity -1 for the derivative. And again, in order to have estimates for the approximation, what I see here, I introduce an additional singularity of -αs and then -αs -1. So what in this case, what the theory will give me is an error estimate in the LP omega C gamma norm of order n to the -r, where r is an exponent less than this quantity here. And if gamma is 0, so in the E soup norm, then I take gamma equals 0 here, then I get r less than 1/2 -1 over p over alpha -1/2. Now, since the initial data was deterministic, I can send p go to infinity, because then I can estimate a fixed LP norm by any p larger than my fixed p. So then I can send p to infinity. So my final result is in this special equation that I considered, is that in the C gamma norm, I get a rate where the rate is anything less than 1/2 -2 gamma over alpha -1/2. So I write this result like this, because if r approaches this, then this constant will blow up. So I will have such an estimate for every r less than this quantity here, where this C depends on r. And then for the E soup norm, I'm going to have a very simple result where r is less than 1 over alpha -1/2. So I will always get a rate in the E soup norm, because alpha is between 1 and 2, so this quantity is always larger than 1, so I will always have a positive rate. And again, if I send alpha to 1, which would correspond to the heat equation, then I will get a rate of 1/2, which is again expected for space-time white noise. So I don't have enough time.
Excuse me. Sorry for interrupting you. Can you go directly to the conclusions? Because
yes.
I think
the conclusion is that we actually done numerical experiments, even for the C gamma norm, and the experiments confirms that what we have calculated is actually sharp. So for this particular example, you can directly simulate the spectral Galerkin approximation on a time grid, and then you can calculate empirical rates of convergence, and then it is very close to the numerical rate. So this confirms that the rates that we got from the theory is actually sharp.
Okay,
so that's the conclusion. Thank you for the
thank you.
attention.
Thank you. Is there any very short question? Only one question, please.
Hi, my name is Pawan. Good presentation. I had some questions on the spectral projection. I see that the error bound is also very classical, that we see it in the usual cases. But I was also wanted to talk about Gibbs phenomena. To my understanding, Gibbs phenomena would also extend in the case of fractional as is. And furthermore, I was hoping to talk about aliasing errors and de-aliasing techniques. Does it extend as classically in the cases of fractional? And my second part of the question is, what do you do for boundary value problem? What are the appropriate basis function in here?
Well, I did not quite understand the first part of the question. The second part is so for example here, so this is a fractional in time equation. And of course, if you have boundary values, then the whole thing becomes a lot more complicated. I mean, even in the deterministic setting. So whatever you can do in the deterministic setting, you can also do this in the stochastic setting. So if you can deal with boundary values, for example, extending them in, and then what I believe that you can rewrite this as say a homogeneous in this case, and adding an extra t-dependent term, which will be deterministic in this case.
I mean, not excluding the stochastic part, let's talk about integer order cases versus fractional orders. For my integer order cases itself for the boundary value problem, I cannot use the but the sines and cosines as the basis function.
I mean, if you have boundary values, I mean, see, this is all based on a linear operator A. So if you have non-homogeneous boundary conditions, then this theory directly is not applicable. So first, then you have to rewrite this equation with an operator that has homogeneous boundary conditions, because otherwise you cannot put the inhomogeneous boundary conditions in the domain, because then it's not going to be a linear space. So then you have to first transform your problem into a problem where the linear operator has homogeneous boundary conditions. But this is what you do. This is what you do in the integer case.
Okay, so thank you. Sorry. Perhaps you can finish later by connecting each other. Thank you very much again, because we are a bit late, and then we move to the next speaker.